This is Learning Assessment Problem 817. The problem-solving strategy here is the application of AC steady-state analysis to complex impedance circuits. We have a single source in this circuit, a phasor representation of that source, and a variety of resistors, inductors, and capacitors connected together. We're asked to determine the voltage V sub O using nodal analysis. We'll choose the bottom of the circuit as our reference node, and we already have this node at the right corner named V sub O, and let's name this top node V1 for use in our analysis. And we do have another node here at the top of the voltage source, but we know that node voltage is a constraint. So we'll continue with the writing of the node voltage equations. So if we do the Kirchhoff's current law at node V1, we'll have V1 as a phasor times the sum of the reciprocals of the impedances, or the sum of the admittances of all the terms connected to that node. And then we subtract the other ends of those impedances as voltage is divided by impedances. So in one case we have the voltage source 12 at an angle of 30 degrees divided by 2 ohm resistor. And then we have this voltage which we're interested in, V sub O, divided by minus J1, representing that capacitor connection. And this sums to 0. Or we can gather terms and say this is 1.5 plus J 0.5 V1 minus J 1 times VO is equal to 6 at an angle of 30 degrees amperes. So that will be one of our node voltage equations. If we do a Kirchhoff's current law summation at the node VO, we'll have minus V1 divided by minus J1 plus VO times the sum of the connected elements, 1 over 1 ohm plus 1 over minus J1 ohm. This is equal to 0, or in rearranging those terms we have, or rearranging that equation, we have minus J1 times VO rearranging that equation, we have minus J1 times V1 plus 1 plus J1 times VO is equal to 0. That's our second node voltage equation. And we can take the coefficients of those equations and put them into a matrix format. So we'll have 1.5 plus J 0.5 minus J1 minus J1 and 1 plus J1. This is the admittance matrix. We multiply that times the voltage matrix, V1 and VO. And this is equal to the currents, 6 at an angle of 6 at an angle of 30 degrees, 0. So we can solve this matrix equation. We're really interested in the VO term here. We can use the Cramer's method. The determinant of the elements in the admittance matrix is 1.5 plus j 0.5 times 1 plus j 1 plus 1 for the other cross product term. This is equal to 2 plus j 2, which in polar form is 2 square root of 2 at an angle of 45 degrees. Again, using the Cramer's method, we'll solve for VO in this matrix form, and we have 1.5 plus j 0.5 minus j1. The current's 6 at an angle of 30 degrees and 0. That is a determinant, and we divide that by this delta determinant to obtain the expression for VO. And this is equal to plus j 1.6 at an angle of 30 degrees divided by 2 square root of 2, angle of 45 degrees for the delta determinant. So V sub O is equal to 1 at an angle of 90 degrees for that J factor times 6 at an angle of 30 degrees divided by 2 square root of 2 at an angle of 45 degrees. And this is equal to 2.12 at an angle of 75 degrees volts.